Okay, anything else? All right, our scheduled lab was vacuum filtration of our crystals today, but turns out we don't have enough vacuum filtration apparatus. And so what we'll do is we'll push the filtration to Tuesday, and then we'll end up moving the Le Chatelier's lab that was scheduled for Tuesday to Thursday. This is a short lab, so we'll do both lab and exam on Thursday. Today I'm going to finish up chapter 13, and we'll do a little bit, we'll check on our crystals later. But there are ways to manipulate the driving force, and so some of the ways that we encounter temperature. Temperature is obvious. We can try increasing or decreasing the temperature to manipulate the driving force, delta G. We could also use coupled reactions to manipulate the driving force. But what exactly is the driving force? Normally when we think about the driving force, okay, it's negative, it's spontaneous. If it's positive, it's non-spontaneous. And we can take a look at the reaction that we were looking at yesterday with the copper, and see what we have here is the 2 copper pluses plus the tin 2 plus. This goes to 2 copper 2 pluses plus tin 4 plus. If we take some experimental measurements, then we see that where this ends up, it doesn't matter where it starts. If you look at Q, there's no pattern there. Q was the initial ratio. And so the initial ratio could be anything. It could be infinity or 0, anywhere from 0 to infinity. And that initial ratio was the ratio of the products, over the reactants. So we could start anywhere here. But, at the end of this, the ratio that we should end up with was 1.486 based on those 3 experiments. We don't know which experiment was the best, so we'll just average the 3. We get something like that, 1.486 or so. And so what can we do with that? Well, what we can do with that is we can do some calculations here to figure out. Actually, where did we end up? Where did we stop yesterday?
Right, we're solving for x.
Yeah, so that's
Okay, solving for x. All right, so we have an equation for solving for the x, and it's 1.486, and it's going to be the products raised to the respective power over the reactants. So the products this is going to be 2x squared. That was the equilibrium concentration of the copper 2 plus. The equilibrium concentration of the tin was just x, and that's raised to the first power. What was the equilibrium concentration of the copper plus? And so this was the initial. What was the initial concentration? 0.348. And then there was a change. We're going to lose minus 2x. We don't know what that percent change is, so we'll just leave it as 2x. And we'll put that in here. It's 0.348 minus 2x, quantity squared. And then what was the initial here on the tin?
0.127.
127 minus x. Putting that in here, 0.127 minus x. Now for the units, we're not going to include the units, and there's a reason for that I'll talk about later. But, I can do some algebra to maybe try to simplify this, but it looks like a pretty tough problem. Did anybody solve it? Anybody solve this? The algebra? No. Probably. So what we're going to going to do is we're going to do the guess and check method, or the method of successive approximations. And so we're just going to do a guess. We're going to guess x and then check what k equals. You know, k is supposed to equal 1.486. That's what we should guess. And so what should we guess for x? Well, I don't know. If I look at here, x can be anywhere from 0. So x should be greater than 0, but it should be less than 1.127. We don't want it greater than 0.127. If it's greater than 0.127, then I have 0.127 minus a bigger number is going to give me a negative number. Is there such thing as a negative molarity? Let's say if I need to make some -6 molar sodium chloride. So can you weigh out negative x grams of sodium chloride so I can make a negative molarity? No. And so there's no such thing. So I have to keep the x, my guess, between 0 and 0.127, so it narrows it down quite a lot. And then over here, I cannot have 2x greater than 0.348. You know, 2x has got to be less than 0.348. If it's greater than 0.348, that's going to give me a negative molarity. The negative molarity would require negative grams of copper. Negative grams of copper doesn't exist, so we're going to have this. And so the 2x is going to be there, so that means x is going to be between, well, what is half of 0.348? That would be 0.174. 0. So it looks like, okay, well, I can't have x bigger than 0.127, so I'm going to eliminate this restriction. X has got to be between 0 and 0.127. Now, when I look at this, I look at the ratio. You know, k, the ratio is 1.48. And one way of thinking about it is, if I just oversimplify this, I think 1.5 parts product for every 1 part reactant. And so if I think about it in that sense, then maybe what I'll do here is I'll just try to keep x simple. My first guess for x is going to be like half of it. Well, maybe more than half of it. And so, well, I want to keep the number simple, so I'm going to guess x is 0.1. So that means I'm going to lose more than half. But that's okay, because I don't want to do too much keying on my calculator. And so let's go ahead and plug it in. And so when I do this, I'm going to plug this in. That is here. I'll just plug it in here. I'm not going to further simplify this. It's not worth the time. The numerator is pretty easy. And so I'm going to plug in 0.1 for this, and for this. So I'll start off here. And I'll do the denominator first and then multiply it by the numerator. So I'm going to punch this into the calculator here, which would be 2 times 0.1 is 0.2. And so it's going to be 0.348 minus 0.2 equals, square that, tilt this to get my square, square that, times, all right, 0.127 minus 0.1 is 0.027. So I'm going to go times 0.027 equals that. So I got my denominator. I'm going to invert that, times 0.1 cubed times 4. And so when I do that, I get a k value of 6.763. Well, 6.763 is too big, right? And so maybe I don't need as much product. I got too much product. You know, my change is too big. So let's make the change smaller. And, you know, I want to keep the number simple initially until I narrow it down. So let's just go to 0.01, you know. But maybe that's way too small. What should we do? Should we do that?
Should we do 0.08?
Yeah, 0.01 might be too small. Let's we could try 0.08. How about that? That sounds good. Let's go for that. So 0.08 times 2 is 0.16. So I'll just do that here. 0.348 minus 0.16 equals square that times 0.127 minus 0.08. Oh, I'm going to use the parentheses. I don't want to think too much. 127 minus 0.08, close parentheses, equal, oh shoot. I just screwed up. I had to redo it. So I go 0.348 minus 0.16, unless somebody already calculated it. Square that equals, I forgot to hit the equals, that's nothing, times, okay, 0.127 minus 0.08, what is that, 0.047, I'll just do times 0.047 equals that, I'll invert that, times 0.08 cubed times 4. Somebody have it? 1.233?
Yeah.
Okay, 1.233. It's closer, but it's too small. So it's going to be between 0.08 and 0.1. In other words, so let's see, where do I want? I just want it just a little bit above there. And I think if I want 0.09, that 0.09 would be halfway here. I don't want to go that high. And so what I'm going to do is I'm going to go 0.08 and then just a little bit above it. And so what should we do? 0.085? All right, let's try 0.085. See, although that might be a little bit big, but let's go for it. Let's see. And so I'll go 0.348 minus 2 times 0.085 would be 0.17. So minus 0.17 equals, square that, times, okay, 0.085 would give me 0.042 times 0.042 equals that, invert that, times 0.085 cubed times 4. 1.845 is what I got. So it's a little bit high. We need to drop it down. Actually, so we're at about 1.5, so we're about halfway between these. So if we're about halfway between these, then I'd say if we go from, we want to go closer back down. So we're going to go halfway. So I'd say 0.082. What do you think? Let's try the 0.082. So we'll go 0.348 minus 0.164 equals, square that, times 0.045. Oops. Equals that, invert that, times 0.082 cubed times 4. 1.447. 1.447, we're getting closer. What should we do? Should we go we need a little bit bigger. So should I try 0.083? Or do you think that might be too big? It's probably too big. So let's go somewhere between 820 and 830. And so what do you say? 823? 823? Let's go for that. We'll just try it and see what we can. Or we could go to 830 and then just narrow it down in that range. The advantage of doing 830 is I don't have 3 digits I have to punch in my calculator here. But it's all right. So what I'm going to do is I'm just going to do 2 times 0.0823 equals that minus 0.348 equals, square that, times, the parentheses 0.127 minus 0.0823, close parentheses, equals that, invert that, times 0.0823 cubed times 4. 1.483. 1.483. Pretty much on there, but you know, this would round to 1.49, this would round to 1.48. And so let's just try to get a little bit closer. What do you think? So this was 820, this is 823. And look at how it went up. It went up by about, what, 4? A little less than 4? And so we need this just to go up just a little bit. And so we don't want to, what should we do? And so what do you want to guess here? 0.0825? 824? Well, okay, this went up by 4. So like each digit here that it went up raised this digit up. So I would say 20 is 4, 21 would be 5, 22 would be 6, 23 would be 7, let's say. And so if we went from if we did this, so we need to bring it up just less than maybe 820, 823, and then maybe rather than that, we want half of that. And so 5 might do it. You want to try that? You said 5? It's just a guess. It doesn't matter. Just try it and see. 0.08235. All right, so let's try this out. I'm going to go 2 times 0.08235 equals minus 0.348 equals that, square that, times parentheses 0.08235, 0.127 minus 0.08235, close parentheses, that, invert that, times 0.08235 cubed times 4. 1.489. And so we went from 8230 to 8235, and if you look at this, we went about 6. And so it looks like each one of these raised this by about 1. So if you want to go for 6, then we probably should back it down by 2, maybe. So maybe let's try 8233. Let's try that. Let's see. And so I'm going to go 2 times 0.08233 equals that, square that, times parentheses 0.127 minus 0.08233, close parentheses, equals that, invert that, times 0.08233 cubed times 4. Maybe I screwed up my calculation. Does somebody have it? What is it?
So
1.486. Well, we're not carrying the extra digits, and we don't do a domino rounding effect, so this would be it, even if it's a 6.6. And so, does that look good? Yeah, that looks good. When do we stop? When we stop is, when we hit the numbers here, or, when we go way beyond. If you look at this, I have 3 decimal places in the concentrations. If I keep going, and pretty soon I'm at 10 decimal places, does it even matter? No, because all those decimal places that we worked so hard to get are going to be rounded off anyway. And so normally what I do is, if this is 3, I at least go to 4 decimal places. So I might have stopped earlier, up here. But anyway, we'll go to 5 decimal places here. It's okay. All right, so that's our x value. Did that take very long?
Yeah. Yeah, for tens, yeah.
Did it take very long compared to solving for x? Could you have solved this? Yeah. Well, on the test, I'll tell you, people have tried to solve this and failed many times, even with extra time on the exam. We'll spend 1 hour trying to solve this for x and give up. And so, did this take much time? No, this takes no time. This is easy to do. Some people might get lucky and take 3 guesses. Some people, they might take 10 or 15 guesses, but it doesn't matter, because eventually, if you're persistent enough, you'll just narrow it down. And so I don't worry about the time, because you can be comfortable that you can get the answer without too much difficulty. And so what we'll do with that number is this. What we're going to do now is we can figure out, we started at 0.348 molar here, and over here we started at 0.127 molar. Here we started at 0 molar and 0 molar. And now we can do this. We can figure out the stoichiometry of this problem, because here the copper plus concentration at the end of the reaction, once equilibrium has been established, there's no more change, is going to be 0.348 minus 2x. And so what is 2x? 2x would be 0.16466. 0.16466. Is that right? Just double that. Sorry. All right, and so we'll just subtract this. We're going to get 4, 3, 7, 3, 8, 1. 0.18334 molar here. And so what percentage of the copper plus reacted? What percentage is, we know the change now. The change is minus 2x. So the change is going to be minus 0.16466 molar. And so we started off at 348. We lost 164, 165. What percentage? How much did we lose? And so to figure out the percentage, we take this amount, the amount that was lost, 0.16466, divided by our initial, 0.348, and then convert that into a percentage, 47.3%. And so we had 47.3% reaction. We didn't have 100% reaction in this case. Just 47.3% of our copper reacted. All right, now going over here, we started off with 0.127, and we're going to lose x, which is minus 0.08233. So let's carry some extra zeros there. So this is going to be 7, 6, 4, 4, 1, 0. And so here we started off at 0.127 molar, and by the end of the reaction we're down to 0.04467. What was the percent reaction of the tin 2? Can you calculate it for me? 34.6%. So this is a 34.6%. Which one was the limiting reagent? Looks like tin 2. Actually, is it the tin 2? 2, Yeah, 250, yeah, so tin 2. So what we'd say is that there's 34.6% reaction here in this particular experiment. And then 2x, we calculated before, it's 0.16466 molar. And then x is 0.08233 molar. Now, how did we figure these out? We figured these out because the ratio of products to reactants at the end, at equilibrium, has to equal 1.486. So this gives us a way to double check our calculation, just to make sure I didn't make any subtraction errors here or any other errors. I can do a quick double check. And that is, I double check it by calculating K using the equilibrium concentrations that we just calculated. And so let's go ahead and do that. K is going to equal, okay, the copper 2 concentration at equilibrium, 0.16466 squared, times the tin 4 concentration at equilibrium. So,
might it be 0.183?
well, for the products, I'm doing the products.
Oh, products.
Products
Sorry.
over the reactant. And so this would be 0.08233 raised to the first. Now we'll do the reactants, which would be 0.18334. This has to be squared because of the coefficient, times 0.04467. The reason I'm carrying extra digits here is because I want to minimize round-off error. When I do the double check should equal 1.486, but if it doesn't, and it's off, it could mean one of two things. It could mean it's off because of round-off error, or it could mean that it's off because I made some other more serious error in my calculation or setup. And so let's go ahead and calculate this and see what we have here. So I'm going to go with 0.16466 squared times 0.08233 divided by 0.18334 squared divided by 0.04467. And I get 1.486, so it's good. Now sometimes this is off because of round off. Again, sometimes it's off because of other means. So if it's off a little bit, it's likely due to round off. If it's off more significantly, it could be due to extreme rounding, or it could be due to, which you shouldn't do extreme rounding, or it could be due to it could be due to a setup error. What I mean by extreme rounding is, some people round. I don't know why, but it happens. Once in a while I get somebody who'll round this number. They don't like 0.18334, it's too much writing. So they'll just round it to 0.2. If they round it to 0.2, what's that going to do when we go back and double check it? The numbers are going to be so far off that we start to worry, did we make a more serious error? Okay, so that gives us a way to tackle, in fact, we got to use this quite a lot this semester, the method of successive approximations, because the algebra isn't so simple. Now, how does this relate to delta G? Did we calculate delta G for this reaction already? Did we calculate a delta G value? I think we did, but how are delta G and K related? They have to be related in some way. because delta G is going to tell us about this, the seesaw, in that way. What's favored, reactants or products. And so let's take a look at delta G naught and K. It turns out when we look at the relationship between delta G naught and K, I'm not going to go through the derivation of this, but we'll see that delta G naught is equal to minus RT ln of K. And so we can see that K and delta G naught are related to each other here. And so an example of this is, what do you think about the delta G here? The delta G naught here, we can calculate based on our K values. So delta G naught is equal to minus R, which is going to be 8.3145 joules per mole Kelvin, times T, which is at 298 Kelvin, times ln of K. And so it's going to be ln of 1.486. And so what does this give us for our delta G naught? Well, here, I'll probably do this first. 1.486 natural log of that, using this kind of calculator, times 298 times 8.3145, 981. I'm going to convert this into kilojoules because delta G is normally in kilojoules. So this comes out to negative 0.9813 kilojoules per mole. And now, if you have a delta G naught of minus 0.98, around minus 1 kilojoule, is that it's negative, so it's spontaneous, right? This reaction is spontaneous, but is that a big driving force? What would you say? No, that's a pretty small driving force, and so the driving force is pretty weak. We'd expect the driving force to be pretty weak because, as you recall, there isn't a huge difference in stability between the reactants and products based on the strengths as oxidizers and reducers. And so this makes sense. This makes sense that there's going to be, a mix of reactants products. One side isn't heavily favored over the other. Since one side isn't heavily favored over the other, then the product to reactant ratio comes out to about 1, or close to it, 1.5 to 1 or 1 to 1, as we expect. And so that's going to result in this type of scenario here, where we have significant amounts of reactants and products present. And so that's how we can connect the delta G and the K. So we should do some more of that. And so let's take a look at some delta G naught values. Like, for example, if I had delta G naught value of plus 200 kilojoules, what do we say about that? Plus 200 kilojoules means it's highly non-spontaneous or highly spontaneous? It's non-spontaneous. That means the reactants want to stay as reactants, and we don't expect much product to form. And so let's go ahead and calculate the K value for this. The K is going to tell us the ratio of products to reactants. Essentially. It's tricky because there could be squared terms or cubed terms, but just in general, it's products to reactants. And so how do we calculate K? Well, we've got to rearrange this equation over here. K is equal to, we're going to use some of the properties of natural logs. We're going to say K is equal to E to the minus delta G naught over RT. And so let's go ahead and plug in our delta G naught and make sure everything cancels correctly, and then calculate the K. And so we'll do the first one here. K is equal to E to the minus delta G naught, so that's going to be minus 200 kilojoules per mole, divided by R, 8.3145 joules per mole Kelvin, and T, 298 Kelvin. And so when I look at when I look at this here, the Kelvin cancels, the moles cancel, but the kilojoules and joules don't cancel. And so I need to convert one of these. I'm going to convert kilojoules to joules. So I'll multiply it by 1,000 joules per kilojoule. Okay, now the kilojoules cancel, the joules cancel. So we're left. Okay, so this is going to be 200, negative 200 times 1,000, divided by 8.314, 5, divided by 298. All right, I get negative 80.71, and then I'll raise e to that. And the k value is 8.79. Actually, I'm not doing sig figs here. This is exact. So 8.790 times 10 to the minus 36. So if you have a 10 to the minus 36 ratio, that means you have one part of, let's say, one part product and 10 to the positive 36 parts reactant, roughly. And so do you see this is heavily biased? This is all reactant, basically, very little product. And so let's go to plus 50. If we go to plus 50 kilojoules, what's my K equal to? It's 1.72 times 10 to the negative 9?
Yeah.
Thanks. All right, this is getting a little better. You know, now we're going to form a little bit of product, but it's still like a 1 to 1 billion ratio. We have a 1 to 1 billion ratio, 1 to a billion, 1 part product, billion parts reactant. That's not much reaction, right? And so this is still highly non-spontaneous. If we get a delta G naught of 0, if I have a delta G naught of 0, what is my K? 1. And so if delta G naught is 0, then I have more like a 1 to 1 ratio of product and reactant. Minus 50 kilojoules we say is spontaneous. Right? And, it would be highly spontaneous. What would the ratio be here, product to reactant? 5.81 times 10 to the positive 9? Or 8? Positive 8, was it?
8.
Yeah, okay. And so, yeah, that's close to 1 times 10 to the 9. And so it's about a billion parts of product to 1 part of reactant. And so let's go to minus 200. If we go to minus 200 kilojoules, what's the ratio? .04 times 10 to the 35. 1.14? That's huge. So this heavily biased towards. And so we see these driving forces, and then we see these driving forces related to these final equilibrium ratios that we should have for product and reactant. But when we look at this, let's go back to this equation here. Let's look at this equation in a little bit more detail. And that is, what does this mean here? That means standard conditions. And standard conditions consist of what?
1 bar.
Yeah, 1 bar or 1 atmosphere or 1. What's the standard concentration? 1 molar. There's a standard concentration of 1 molar. Do you guys remember 1.486? 1.486 is the number we came up with. K is equal to 1.486. And that was based on 3 experiments. The first experiment, we started with 0.100. 0.100. We ended up with something else, like 0.03 or something like that. The second experiment, we started off with 0, 0, and 0.100. And third experiment, we had 0.100s all the way across. Were any of those under standard conditions? None of them were under standard conditions. So could we use this? I just plugged in 1.486, but that 1.486, can we use it? Because none of those experiments were under standard conditions. And I'm saying that delta G under standard conditions is equal to minus RT ln and K, but we use it. And yeah, the answer is yes, we can use it because, you know, what is this driving force that we're talking about? The driving force depends on this. When we see something like this, the way I visualize something like this is like this. If I'm looking at my 2 copper pluses plus a tin 2, and I want to do this under standard conditions, this is going to be 1.00 molar, this is going to be 1.00 molar. Or actually just 1. It's supposed to be 1. So 1 molar, 1 molar. But not only do the reactants have to be at 1 molar, it turns out if I want to do this under standard conditions, all the concentrations must be at 1 molar. And so that means the products, the 2 copper 2 pluses and the tin 4 plus, it turns out to be under standard conditions, these have to be 1 molar as well. Now I'm under standard conditions. And so I have standard conditions here. Is it going to stay under standard conditions? I mean, what does this 1.4866 mean? What does that delta G negative mean? It means that there is a driving force for this. And so when I see this, I say, okay, starting under standard conditions here, is there a driving force for reaction? And it turns out there is, because what is my Q here? Under standard conditions, my Q would be equal to the ratio of products over reactants. So if I calculate my Q, which is the initial ratio, I get 1 squared times 1 divided by 1 squared and 1. And so if I look at my Q under standard conditions is 1. Now my Q is 1. Am I at equilibrium? No, this is not the right ratio. In fact, I need some reaction to occur. The reaction how much reaction do I need to occur? I just need a little bit of reaction to occur, because remember, it's more like a 1.5 to 1 ratio. Not exactly because of all the squared terms, but it's close to it, because here we have a 1 to 1 ratio, right? And so if we push it a little bit, just a little bit, then we're going to hit that right equilibrium. In fact, we just need to go from a Q equal to 1 to a K equal to, or 1.486. And so there is a driving force. There's a little bit of driving force to go from our standard initial conditions to a 1.486. Is it much? It's not much. The driving force is -1 kilojoule. That's my driving force for this, because it was -0.9, which will just round to, it's close enough to 1. Here, about -1 kilojoule. And so I have a little bit of driving force because I need to make a little bit of product to increase the ratio a little bit. Now, it depends on where you're starting. You know, if we're starting with all 1s, then yeah, I'm going to see a driving force. But what if I didn't? You know, what if I have the right ratio? Let's say initially I make the ratio 1.48. You know, so now I'm going to start under non-standard conditions, and my non-standard conditions, I just mix this up. Hey, the ratio is already 1.486. Is there a driving force? Here. No, actually, there's no driving force because I'm supposed to be at 1.486. I'm already at 1.486 with these concentrations, so no driving force. And so this is what we think. You know, we have to have some kind of starting point, an initial starting point, and that's going to tell us, do we need to make more product? Do we need to make more reactant? It's going to tell us if delta G is negative, we need to make more product. If delta G is positive, we may need to make more reactant to bring the ratio to what we need. Here, this is the ratio that we need. And so this is where we're starting. So it's like a drive, you know. How long of a drive does it take you to get to school? Well, you know, it depends on where you start. If you're already at school, then there's no driving force. You don't have to drive. But if you're far away, then you have to drive. And so the standard conditions is, well, how about everybody starts at this point, you know, and then we'll see, and we can make a fair comparison. And so that's what we're doing here. And so it gets confusing sometimes because when we end up at equilibrium, we're nowhere near standard conditions. When we end up at equilibrium, you know, if we're under standard conditions at equilibrium, it's not 1.486, it would just be 1. Right? And so people get confused by this because they think, yes, the concentrations have to be 1 molar, but they certainly aren't 1 molar to get here. All right, now this is what we're going to do next. So that's kind of relating driving force and this equilibrium mixture that we're going to have at the end, you know, how we can do Chem 1B stoichiometry. But there's ways to manipulate the driving force, and we did that. You know, we looked at delta G naught and manipulating that. One of the ways we did that was with temperature. You can increase or decrease the temperature, you can change your delta G naught. This is going to change driving force here. Now, we looked at coupled reactions. You know, if we use coupled reactions, we might be able to synthesize a product, specific product that we're interested in. So delta G naught in coupled reactions. But that's kind of where our options end here. What we can try to do next is we can try to go non-standard. And so if we go non-standard and we do this at 298 Kelvin, then how do we deal with that? And so delta G under non-standard conditions is going to equal delta H under non-standard conditions minus T delta S under non-standard conditions. Well, do we have a table of delta H and delta S values under non-standard conditions? Unfortunately, we don't have this data. And so we have to think of another way. Is there another way? Because this is not in Appendix D. And it's unlike changing the temperature, because if you change changing the concentration and changing the pressure could have a significant impact on this, perhaps. And so the other way of doing this is we could try this. And it turns out that delta G, we can use delta G under standard conditions and then just correct it with a factor, RT ln of Q. This is where Q is the reaction quotient. Q is what we talked about before. Q is just the ratio of the products raised to some power over the reactants raised to some power, or reaction quotient. So one thing we could do is we could do this. We could do this at 298 Kelvin because we can calculate delta G naught at 298 Kelvin. And then R we know, T we know, Q we can manipulate what Q is. Well, how do we manipulate what Q is? Well, Q, let's talk about this in more detail. Q is the same thing as K. Q is usually the initial concentrations of the product and the reactant. K is the same thing, except it's the equilibrium concentrations of the product and the reactant, raised to their respective powers. And so let's see what these values are. If I have all solutions, then typically when I look at Q or K, I'm just going to use K, or I could substitute Q here. Q or K is equal to, okay, all solutions, we're going to look at the concentrations. Now I'm going to write a generic equation. My generic equation is going to look like this. It's going to be AA plus BB plus dot 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 goes to GG plus HH plus dot dot dot. And so I'll just take my products. And so the first product would be G, and the coefficient is little g, and so I'll raise it to little g power. My second product is H, capital H, and the coefficient is little h. And so I just do that for all the products, and then I'll go to the reactants. And so the reactants would be A raised to little a, B raised to little b, etc. And then we're going to label this. This is QC or KC. The C stands for concentration. That's what we do. But if we're dealing with gases, we can do concentrations of gases. That's not a problem, moles per liter. But usually what's easier is to do pressures of gases. And so if we have all gases, then we know that P is equal to nRT over V. If I look at N over V, N is moles, V is liters, moles per liter is molarity. And so if I look at this, this is going to equal the molarity times RT. And so what this says is that the pressure and molarity are directly proportional to each other. RT, once I fix the temperature, is a constant. And so pressure and molarity are directly related. In fact, they're directly proportional to each other. And so what I can do is I can express this ratio in terms of pressure rather than express the ratio in terms of concentration. And so I'll have something called QC or KC. And QC or KC will be in terms of partial pressures, which sometimes is easier. And so I'll have the partial pressure of G raised to little g, partial pressure of H raised to little h, dot, dot, dot. And then partial pressure of A to the A, B to the B, dot, dot, dot. And so I can use partial pressures instead of molarities. The relationship between Kc and Kp we can derive here, because the partial pressure of G is equal to the molarity of G times RT. And so what I'll have here is that the partial pressure of G equals the molarity of G times RT. I'll just substitute that in here and then raise the whole thing to little g. And then all over here, the partial pressure of H is equal to the molarity of H times RT, and then raise the whole thing to the H power, dot, dot, dot. And then I'll go over here, I'm going to put A, concentration times RT raised to the A, and B, the concentration times RT raised to the little b, dot, dot, dot. And then I'm going to factor out the RT, the numerator and the denominator. If I factor out the RT, I'm going to get G raised to the G, H raised to the H, dot, 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 times RT. Okay, now I'm going to just add it. RT to the G times RT to the H is going to just be G plus H plus dot, dot, dot. And then down here, I'm going to have the concentration of A raised to little a, concentration of B to little b, dot, 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 times RT. And this is going to be A plus B plus dot, dot, dot. There. And so what I'm going to get here is I'm going to get the Kp is equal to, well, the first term there is Kc. So Kp is equal to Kc times RT. And what I'll do is I'll just do this. If I look at the GHI, that's the sum of moles of gas of the product that would be G plus H plus I, minus the sum of the moles of gas of the reactants. The reactants would be A plus B plus C. And so what we're going to call that is it's going to be Kc RT to the delta N of gas, where delta N of gas is the moles of gaseous product coefficients minus the moles of gaseous reactant coefficients. And so we can use a Kc or a Kp, they're related to each other. And when delta N of the gas is 0, then Kp and Kc are equal to each other. Then what do we have when we have heterogeneous mixture? And so if we have a mix of states, then we have to use something called KEQ or QEQ. Now KEQ is the K that was in all the thermodynamic equations. QC and QP, QC and QP and KC and KP, these are from experiment. QEQ and KEQ, those are going to come from the equations of thermodynamics. And so for QEQ and KEQ, we do this. When we write out the expressions, we're going to ignore pure liquids and pure solids. The reason for that is because pure liquids and pure solids, the concentration doesn't change. So let's start off with some pure aluminum. If I have some pure aluminum, it's 100% pure. So let's say I have a pound of aluminum. If I have a pound of aluminum, and it's 100% pure, I gave away half a pound. Let's say somebody needed some aluminum, I gave them half a pound of aluminum, I'm left with half a pound. Did its purity go down? Did its concentration go down? No, it's still pure. It's the same thing with water. Do you know what the concentration of water is? In molarity, moles per liter. If I have a liter of water, it's 1,000 grams. 1,000 grams is 55.5 moles. 55.5 moles per liter. Therefore, pure water has a molarity of 55.5 molar. So if I have a bottle of water here and I dump out half the bottle, did the molarity go down by half? Or is it still 55.5 molar? It's still pure water, right? I just don't have as much. And so when I'm looking at reactivity, I care about concentrations. And so for example, if I'm looking at this reaction, aluminum plus 3 HCl, that's going to give me aluminum chloride. This is aqueous, plus 3/2 H2 gas. Here. And this is heterogeneous because I have a mix, solids, aqueous, gas. I could have liquids in there, same type of deal. And now when I look at the K or the Q, you know, the K here is going to be this. If I have aqueous solutions, I use the concentration. And so this is for KEQ. And so AlCl3, I'm going to use the concentration. If I have a gas, I'll use the partial pressure. H2 gas, this is going to be raised to the 3/2 power. Okay, divided by, now if I have a pure solid, I'm going to omit that from this. And then I have a solution. For solutions, we use the aqueous concentration. I'll cube that. And so here, we're going to ignore the pure liquids and pure solids. But what we're going to do is, for solutions, use molarity. And for gases, we'll use partial pressure, use pressures. Now, we really don't completely ignore it. The situation with aluminum is its concentration changing? So let's say I have a pound of aluminum and I'm eating some of it away. As aluminum is reacting, does its concentration change? Does it become more or less concentrated? No, its concentration stays the same. And since its concentration stays the same, it doesn't have an impact on the driving force, because what it's going to have an impact is like this. For example, if I use 0.1 molar HCl versus using 16 molar HCl, is there a difference in the driving force? 0.1 molar HCl versus 16 molar HCl. Which one do you think is going to have a bigger driving force? It turns out the 16 molar HCl will have a bigger driving force. It's going to be more reactive. And so, since aluminum doesn't change, we say its activity doesn't change. And so, if we go into deeper into thermodynamics, as we get deeper into thermodynamics, then it turns out that KEQ, which we call the thermodynamic equilibrium constant, is equal to the activities of the products. So it would be the activity of G raised to little g, activity of H raised to little h, dot, 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 over the activity of A raised to little a, activity of B raised to little b, dot, dot, dot. And so I'll ask you, do you remember what activity is from Chem 1A? Anybody remember activity from chapter 14? No? What activities are, A is equal to the activity. And what activities are, these are what we call the effective concentration. The effective concentration, what happens is sometimes the solute particles like each other. Sometimes there's some favorable interactions, intermolecular attractions between them. And so this happens, let me give you an example of effective concentration. Some carboxylic acids are prone to doing this. Because of this, this carboxyl group here, what can happen is this acid molecule should just be floating independently in water. But it might come across another molecule. And if this other molecule is oriented in just the right way, this is R is where if this other carboxylic acid is oriented in just the right way, take a look. This hydrogen can hydrogen bond to this oxygen. This hydrogen can hydrogen bond to this oxygen. So do you see these two hydrogen bonds here? Now each hydrogen bond is about how many kilojoules, just roughly? Yeah, let's say 25 kilojoules. If we got two hydrogen bonds, it's 50 kilojoules. There's 50 kilojoules of energy holding these two molecules together. Is that significant or not significant at all? That's significant because the weakest covalent bond is about how many kilojoules? The weakest covalent bond. So this is 50 kilojoules. The weakest covalent bond is how many kilojoules, roughly? Like 100 kilojoules. And so all of a sudden, this attraction seems pretty strong. What we form is we form something called a dimer. Because what happens is these are no longer independent of one another. And in fact, once they kind of pair up, it forms a pair. And this pair acts as one unit rather than two separate units. That's going to have a significant impact on the colligative properties. So dimerization is a problem because you might start off with 1 molar, but its effective concentration is like cut in half because half the molecules are taken out because they're pairing like this. And so sometimes we'll treat it like one unit. It depends on how strongly bonded they are. For example, is DNA 1 molecule or 2 molecules? Or 4 molecules? What is DNA? Is DNA 2 separate molecules or is DNA 1 single molecule?
2.
Double-stranded.
Double-stranded. And if it's double-stranded, is it like two separate strands? Is one strand here, one strand here? They're two separate, or is it just one strand?
Two separate.
Is it two separate, or does it act as does a DNA molecule act as one molecule, one long molecule, or is it two separate molecules, independent of one another? It acts like one. Why? Because of all the hydrogen bonding interactions that are holding it together. If you turn off the hydrogen bonding interactions, then they separate apart. If there's some switch, we can flip this off, then these can break apart, right? So right now they're held together. Well, if you look at DNA, DNA is held in the helical structure by hydrogen bonding interactions. Otherwise, if there weren't those, then it would fall apart. I don't know if it's two or one or whatever, but sometimes things don't behave as two independent, and so this would be it. And so activities, we got to worry about the activities. And so some things will make the activities deviate significantly from their concentration. However, if we use fairly dilute solutions, then there's no problem. And so what we're going to say is that the activity of a solution is close to its concentration, and the activity of a gas is close to its pressure. And the activity of a solid, its activity doesn't change, so it's got unit activity. And the activity of a pure liquid, that doesn't change either. I mean, if I have a gallon of pure water and I lose half of it, I still have a half gallon of pure water. Its activity doesn't change, it's still pure. And so when we do this, you know, when we do something like this, then really what we do is this, but we skip a step. And so we go KEQ is really the activity of aluminum chloride AQ times the activity of hydrogen gas to the 3/2 divided by the activity of aluminum solid and the activity of HCl AQ cubed. And so we say, well, that's an aqueous solution, so we're just going to say it's going to be close enough to AlCl3. Hopefully there aren't too many of these pairing interactions here. And not only do we form pairs, we can form clusters as well. And then this is a gas, so we'll just say times the pressure of H2 to the 3/2 divided by the activity of aluminum. The activity of aluminum is 1, and the activity of HCl is the concentration of HCl. And then this would be Q. All right, so what we can do is we can change, you know, because what we see here is that delta G is equal to delta G naught plus RT ln of Q. And this is QEQ. QEQ is this. And so we can change the activities of the reactants or products to try to get this driving force to go or change the driving force or whatever. And so we're going to play with QEQ, that is, play with the activities to see if we can change our overall delta G here. And so that's under non-standard. Now there's a trick to this. This is going to be delta G and non-standard conditions at 298 Kelvin. At 298 Kelvin, because delta G naught, how do we calculate delta G naught? We calculate delta G naught at 298 Kelvin. Now, if we look at delta G in non-standard conditions at a temperature T, then this is going to be at 290 Kelvin. And then we're looking at delta G at temperature T, which is equal to delta G naught at temperature T plus RT ln of Q. Now the problem is how do we get delta G naught at temperature T? How we get delta G naught at temperature T is by making the assumption, right? We make the assumption that delta G naught at temperature T is equal to delta H naught at temperature 298 minus T delta S naught at 298. And so that's reasonable. But we cannot do this. We cannot say that delta G naught at temperature T is equal to the sum of the delta G's of formation of the products at 298 minus the sum of the delta G's of formation of the reactants at 298. Because this will give us delta G naught at 298, which is not the same thing as delta G naught at temperature T. So we have to be careful there. What we can do is we can do two separate calculations. First we calculate delta G naught at temperature T and then plug that in here. Or we can just combine these into one equation. Sometimes we combine these into one equation because we're after a desired, something that's desired. So sometimes we need to solve for T. So what we can do is we can do delta G and non-standard and T at T. Now we solve for T. We have to be careful when we solve for T because it seems like it's easy. You know, for example, if we did delta G naught at temperature T is equal to delta G naught at 298 Kelvin plus RT Q, EQ. Can we solve it for this T here? So T is equal to, let's see, subtract, this would be delta GT minus delta G naught of 298 over RQ, ln Q, R ln and Q. Does that work? No, that doesn't work because these T's aren't matched, so this is not going to work. So if I solve for Q, let's say this one was solving for Q, and then figuring out what activity we have to manipulate. If we need to solve for T, then we have to do a little more work. This is going to be delta G at temperature T, which is going to equal delta G naught at temperature T. The problem is do we know what the temperature is? If we're solving for T, T's are unknown. So if we're solving for T, does that make this impossible? Because in order to solve this equation for temperature, we need to know what delta G naught is at that temperature. And in order to get delta G naught at that temperature, we have to plug in the temperature here. So how can the temperature be unknown? Well, what we can do is this. We know that delta G naught at temperature T is equal to delta H naught at temperature T minus T delta S naught at temperature T. And we got that for delta G naught at temperature T. This is going to be minus RT ln a Q. Now we can do this because now we've gotten the temperature term out of this here, and we have it here. And so what we'll do is this is going to equal delta H naught minus T delta S naught minus RT ln a Q. And what I'll do is I'll factor out the temperature out of this side. So we're going to get delta H naught minus delta S, minus delta S naught plus R ln of Q times T. Now we can solve for T. Because what we can do is we can assume that delta H is at 298 and delta S is at 298, and so we're okay. And so we'll just say et cetera. And so what we're going to do today is, since we aren't doing lab, we're going to do some calculations. And so let me write down the calculations that we're going to do on the board here, and then we'll take a break and we'll start again. But so this is going to be in-class assignment here. And we're going to go back to this, and we're going to try to manipulate the driving force of this. So we're going from H2O liquid to H2O gas. And I know under standard conditions at 290 Kelvin, there is no driving force for this. Delta G naught is greater than 0. And so what we're going to do is the first calculation I want you to do is determine the temperature required, in other words, determine the temperature at which the above goes spontaneous. Well, you know, the temperature at which the above goes spontaneous is the temperature at which it boils. So I want you to determine the temperature at which it boils using thermodynamics. Actually, we already did this. You just look in your notes. But I want you to go through it and then analyze it, because we're going to do a very similar calculation. What we're going to do is this. We're going to make this spontaneous at room temperature. Make this spontaneous at room temperature, which is 298 Kelvin, by using non-standard conditions. And so what you're going to do, you're going to tell me, you know, under what conditions will this go spontaneous? In other words, what I'm asking you here is, how can you make water boil at room temperature? Is it possible to make water boil at room temperature? Yes, it's possible to make water boil at room temperature. Use thermodynamics to tell me how. And then 3, we're going to do a combination. We're going to use non-standard conditions and a temperature not equal to 298 to make water boil. And so number 3, I'll put up. Liquid to H2O gas spontaneous. So once some people finish number 2, I'll put up the conditions for number 3 here. And so you can take a break.